Here we go. All right, so this is the second lecture. And like I said last time, I posted last time's lecture on YouTube. You can get to it with this link right here. And I think that's working. If there's any trouble, let me know. And I'll continue to do that through the course and just publish each recorded lecture. So half of you have started this lab on the command line, and the other half will start that today, perhaps. And that is due this Friday, so you need to submit that, get that done by Friday. Today, what I want to talk about is the material that's behind the second lab, which is called, I use the word expressions. So how do you form expressions? What do expressions mean? Before I do that, I want to just go very briefly over this schedule. So we have this lab, which is due next week. You don't have to wait to start on the next lab. You can start that today. You can start at any time. You can work at home, whatnot. Yeah.
If we're not in the class yet, can we turn in the labs anyways?
Say it again.
If we're not in the class yet, can we turn in the labs anyways?
Like if you're on the waiting list?
Yeah.
I think you should wait till you're in.
Right.
And a late submission won't be a problem in that case. Just let me know, okay? And so you've got the sequence of labs, and it's a lab, but it's just an activity. It's a project. You need to do it. You don't have to be in the lab to do it, and it generally takes longer than the lab time anyway. So you can expect to work outside the lab on these problems, and you'll see it's just a list of exercises here to do, and we'll go over that today. And then it's leading up to this exam 1. Oh, these are not visible. I'll have to make those visible. Okay, good I checked that. So I'll list some previous exams. You know what I did? It's the problem is this. That's not it either. Okay, I'll figure that out. So I'll get copies of last year's exam up there for you to look at. All right, let's go into this lab, which covers this topic called expressions. And here's a list of things that you need to learn about. So let's talk about these. And I'll talk about these as in the context of writing some simple programs. Right, understand the notion of a data type. Let's talk about that. Distinguish between the data types int and double. Okay. So, and I'm going to experiment now with this new platform called Cloud9 that I'm using for the first time in this class. C9.io, and these are my workspaces. Here's a workspace I created last time, CSE 201. And here's my lab 1 work right there. I don't need this, I can delete that. I'm going to simplify things and close stuff here. And if you see down here, this print working directory, it shows the path to my workspace. And this view right here is the workspace. So inside this workspace folder, which is under home/ubuntu/workspace, inside that workspace folder, there should be another folder called CSE 20, oh, I'm sorry, CSE 201, I believe, is the workspace folder. Let me check that out. Yeah. So this CSE 201 is the workspace folder. So it's a little confusing. It shows it here as CSE 201, and in this view, it shows it as the name workspace. Well, as you can see, there's a README file in there and a Lab1 folder. There's the README file, and here's the Lab1 folder. Let's create a new folder called Lab2. So make directory Lab2. So see, I'm working at the command line, but the view of what I'm doing in the file system is also available graphically through the graphical user interface. We could have created it here as well. Let me show you that. If I do ls, you see here's the two lab folders and the README. I could create that lab folder here. Oops. Let's see, how do I do that? File. I think there's a new folder in there somewhere. If I right click in here, there it is, new folder. I had to right click in that white space area right here. Right click here. New folder. Lab 3. So I created the folder now in the graphical user interface. But if I go to the command line and run ls again, you'll see it appears there. So these are just two different views of the same thing. What's the thing that we're looking at? It's called a file system. What's a file system? File system is a hierarchical organization of files. Files are sequences of bytes. And you can see that this, if I use print working directory, I can see on my system where my workspace folder or CSE 201, where that is located in the context of this tree of folders and files. All right, so I can CD into the Lab 2 folder, and there's nothing there. And that's the same as viewing here. See, there's nothing in there. There's something in Lab 1. Nothing in Lab 2. What I want to do is make a copy of the file that's in the Lab 1 folder and place that copy in the Lab 2 folder, and then I'll use that to do my Lab 2 exercises. And just to show you what your work would look like, you've got these exercises. Exercise 1, exercise 2. Let's just take a look at this for a minute. Write a console program that prompts the user for 3 double precision floating point values x, y, and z. Have the program compute and display the following values: the sum of x, y, and z, the sine of x, and so on. So write a console program. So we need to write a program that runs in the console window. And it's going to read 3 values, and it's going to print different calculations. And then we'll have exercise 2 and 3 and so on. But 2 is an exception. 2 is, this is problems taken from old exams. And I want you to practice solving these problems in the way that you will solve them during the exam. So print this document out, and then without a computer, practice coming up with the answers. Right? So that'll be just like taking the exam. So it's good practice to get ready. So you won't be surprised on the day of the exam. But that's an exception. Most problems don't look like that. Most problems look like this first one, where we need to write a program. Exercise 3, write a program. Exercise 4, write a console program, and so on. So normally the exercises are to write a program. And so because there's a lot of programs to write, we need to have a naming convention. So I'll call this one, say, E1, E3, and E4. That's what I'm going to use. You can use a different naming convention if you like, but it should be understandable to myself and Sushmita, the teaching assistant, because we will be evaluating your work. So we need to know what we're looking at. So let's go ahead and normally when you start a problem, you're going to look at old code, existing code. So this is the code we've already seen. Prints hello. So I want to make a copy of this code and then build my solution to exercise 1 from that copy. Now I could copy it in the graphical user interface here. Okay, right click. Something's not working. And then copy, and then go in here, and my right clicking operation does not work well. I'll do this, file, paste, or maybe it's edit paste. There it is. Then I'll change the name to E1, right? Well, that's the way you would normally do it, but I want to show you a different way. I want to show you how to do it at the command line, and you're required to know how to do this, how to do these operations from the command line. That's part of the learning objectives of this class. So that's what the first lab is about, how to work at the command line. So I'm positioned into lab 2 here. There's nothing in the folder, and I want to copy CP from lab 1, main.cpp. How do I get there? I can't just do this. I can't just do that. Lab 1's can't find it. That's because lab 1 is in a sibling folder. I have to go up to my parent, which is CSC 201, and then down into lab 1, and then get the file main.cpp. So that's the first argument of this CP command. And the second argument is the new name for the file. I'm going to call it E1. I'll call it EX1. Maybe that's better. Exercise 1.cpp. So you can see the command there's the command itself, CP, and there's 2 arguments. The first argument is the source, what you're going to copy, and the second argument is the destination. It's the name and location, too, of where you want to make the copy. So I just hit enter on that, and let's take a look here. This should be in here. I don't see anything. Why is it not showing up? Am I in lab 2? Oh, there it is. A little slow. It was delayed, but there it is. You know, we're working on a web interface here, so it's maybe slower than working on your desktop, on your computer directly. All right, so there it is, ex1.cpp. There was some delay there. Just keep that in mind.
So CP basically copies the file?
Yeah, CP copies the file. You can copy other things. You can copy folders too. Let's take a look at this, and I'll close this out. So it's just what we wrote last time. You know, hello. I'll just say, you know, I'm exercise 1. And this is not saved yet. We need to save that. I think it's Command S. That did it. Command S. Or I could do this. File save. So on the Mac, it's Command S. So on Windows, it's, what would it be, Alt S? Something like that. And so here we have the file. Now let's compile it. Now you could actually run it here. If I run this, maybe run with C++. I haven't done this yet, by the way, but I saw some of you do this 2 days ago. Look, I'm exercise 1, so I ran it. Oh, and it opens a new, it opened a new tab here. Do you see that? I'm going to close that out. It's called it created what's called a run configuration. So I can repeat that command again with the same run configuration. Note, oh, you want to compile this with a C++ compiler. That's part of the run configuration. But now I'm going to do ls here and take a look. There's run me star. So I can run me. This, I don't know what the star is. I think it means executable. I'm not sure. I can run me. There it is. I'm exercise 1. Now I'm running it from the command line. So I can compile and run this way. Look at this. Run last ex1.cpp using C++, simple. Or I can run it. I can compile and run it from the command line. But I didn't show you how to compile it here. Like I'm going to remove run me. That's delete. Did you see how that disappeared? So rm is remove. You need to know that command. Now let's compile the program ex1.cpp. It generates a.out. It didn't generate run me. It generated a.out. So it gives a slightly different result when you run it from the command line. Although we could do it like this. We could add -o run me. Now it generates a run me. I don't think I can run me though. Let's see. Oops. Try running that. It does run. All right, I'm going to delete that. Anyway, we have a.out, and you can run it like this. See the // we can't just do a.out. This won't work, unless I don't think it'll work. Command not found. That's because the current folder is not in the search path. When you issue a command at the command line interpreter searches through a search path. I'll show you what it is. It's echo $path. That's the path that the command line interpreter searches. It looks through, and you'll see these things should be separated with semicolons. That's a separator. So these are this string that we see here is a list of semicolon colon. That's a colon. It's a list of colon separated path names. The command line interpreter goes and looks at each path name one after another, tries to find the command that you entered to see if it can find an executable with that name. If it doesn't find it, like a.out, it says command not found. So you have to say, no, I don't want you to search in the path. I want you to look in the current directory, // Dot means current folder. Just saying, hey, command line interpreter, don't search the search path. Just look in the current folder, dot, and look for a.out there and run that. So now it runs. We could add the current folder to the system path, and some people do that. You can add dot to the system path, and then the command line interpreter will then search in your current folder to find commands that you type in on the command line. You can do that if you want to. But it's not the default setup. All right. So let's talk about data types. We can print a number. Now let's print number 3. And after we print the number 3, I'll do this stuff later. Let's just print the number 3. I'm going to run a dot out. There it is. Oh, I'm exercise 1. I didn't save this. Thank you. We're coming to that. I'm not used to using this system. There's a nice command history. If I hit the up and down arrow, I can scroll through the command history, so I can just reissue those commands. Does everyone see what happened? The 3 is right there. And as soon after I print the 3, it then prints the prompt. And that's not great. We want a new line character there. So let's go ahead and, you know, if you look at the code I showed you, this \n, this is a new line character. Oh, and I should tell you that this is a cascaded form of that. I'll do it like this. So we can print 3, and then we print this new line character. Let's take a look at that. Well, that works better. And now after we print the 3, now the console will go to a new line. That's called a control character. It's called, also referred to as a white space character because you can't see it. It's invisible. And a lot of times you'll see it like this. You might see that like that. So you can cascade these operations. Let me show that to you. We get the same result. Same result. But how do you think about that? And this is an important lesson I'm going to give you right now on expressions. How do you read this line? How do you comprehend what just happened here? Let me tell you what the compiler does. There's 2 operations here. It doesn't do 2 operations at once. It does one operation, and then it does the next operation. So the first operation it does is it does this output operation. And it's following a rule. The rule is left to right execution. And so when you have most operators are evaluated left to right. Some operators, which I'm not sure we're going to use any, are evaluated right to left. That does happen sometimes. But most operators are evaluated left to right. So what does that mean for an operator to be evaluated? Well, this is a binary operator. It has 2 operands. It has the left-hand side and it has the right-hand side. Those are the 2 operands for this operator. So this, what I'm highlighting right there exactly, this becomes an expression. So the operator by itself isn't very meaningful. It needs 2 operands. So the compiler sees the operator and it looks for the 2 operands. That becomes kind of like a unit. It's an expression. And expressions are things that can be evaluated. What does that mean to be evaluated? It means to be replaced by something else. Let me give an analogy. If in grade school, when you were looking at fractions, simplifying fractions, you saw 2 over 4. And what did you think to do? And then it says simplify this fraction, or evaluate this. Well, simplify it. So you're going to take out a common divisor of 2, and you'll get 1 over 2. Right? So you're going to write down 1 over 2. 2 over 4 simplifies to 1 over 2. So C out, output operator 3 simplifies to something. It's here, ready for this? It simplifies to C out. So you can think of it as you wrote 2 over 4 and you replace that by 1 over 2. Well, this expression I have highlighted here, you replace that with C out. And now just visualize it. What I have highlighted there being replaced by C out. That C out, that resultant C out becomes the left-hand operator of the second output operator. So this is the left-hand operand of the second output operator. And this \n is the right-hand side of that second output operator. So this is a larger expression. See, this is a sub-expression within this larger expression. The larger expression is more complex. It requires a sub-expression to be evaluated first before the larger expression is evaluated. And what does this larger expression evaluate to? What does it become? What does it get replaced by? Anybody know? No, C out, just like the first one. The output operator, whatever you have in there, the output operator evaluates to its right-hand side. And the reason we do that is because it lets us cascade these operations. So we can have a string of output operations one after another because, you know, each output operation evaluates to its right-hand side. I'm sorry, it evaluates its left-hand side. Sorry about that. I made a mistake there. So the first output operation evaluates the C out. And then the second output operation also evaluates the C out. So that means we can have a third output operation. And a fourth output operation. So we get that ability to cascade operations. That's the rationale behind having the output operator evaluate to its left-hand side. Now, also I showed you ENDL. This is an alternative to new line. That's means a new line character. Now the thing about this operator, I'm talking about what this thing evaluates to, but there's something else to say about it. It evaluates to C out. This output operator evaluates to its left-hand side, but it also has a side effect. The side effect is to, in this case, write the character 3 into the standard output stream. To write the character 3 into the stream represented on the left-hand by the left-hand operand. So you think of it like this. When this thing runs, 3 is written into the output stream, and then this expression that I have highlighted right now is replaced by C out. And that becomes the left-hand side of the next output operation. Now, in the next output operation, we write an end line into the output stream, and the whole expression is replaced by C out, which is not used, which just gets discarded at that point, right? It's ignored. So what this expression eventually evaluates to is not used. But the side effects are what we're after. We want a 3 followed by a new line character. So that's the beginning of how to parse these statements in C++ or any language. All the languages are all work like this. There's something called parsing. You know, like when you give this program to the compiler, It reads it. It parses it. Parsing means it breaks up the program itself is one long string of characters. And it says, I can't deal with that. I have to chop it up into pieces. To understand what you want me to do, I got to chop this thing into pieces and understand the pieces. So it'll start chopping things, like it just chops this. It doesn't look any smaller than that. See out is like an atom, inside a molecule. There's no reason to look at the O and the U. It's the C out itself names something that the compiler understands and it uses that. Just like this 3, that's a literal number 3. That means something. And this output operator is a symbol. It's like an atomic symbol. So these things are parsed. So when the compiler reads this string of characters, which comprise our source code, it chops it into these pieces. That's called parsing. And then it figures out what these pieces need, when they need to run, and so on. To get into any more detail there. All right, so that's kind of the basics of understanding of expressions. Now let's talk about variables. Like in math, you'll have something like x equals 4, right? And I want to print x. I don't want to print 3. I want to print whatever is x. So I want to set this variable x to 4, and then I want to print what's stored in 4. So this will do it. But now the syntax is, this is a statement. This is an operation. I mean, statements can be several operations together, but this is going to be a statement. And statements end with semicolon. Unless they are compound statements, then they can end with a brace. But this isn't good enough because the compiler says, all right, you're saying x here, but I don't know what x is. There's this thing called data types. That's what I'm getting at here. Understand the notion of a data type. So I have these variables that represent values. In this case, x represents a 4. And in math, I know a lot of you are math majors, so I'm going to go ahead and talk about math a little. In math, you've got different number systems. You've got real numbers and natural numbers, right? Or integers. I think integers are bigger than natural numbers. You get integers and then real numbers. There's two different number systems, but the integers can be embedded in the real numbers. Or the real numbers are extended out of integers, something like that. And so the compiler says, well, is x a real number or is x an integer? You got to tell me. And so, in other words, the compiler wants to know the data type, wants to know the number system we're using here. So I want it to be an integer. So I'm going to say int x equals 4. I'll set x to 4, print it out. Here's the 4. I could do operations on that 4. I could say x. I'm going to do what's called assignment here. Whatever's in x, see here you see an equal sign, okay? And I used it up here as well, and I didn't talk about it. It's an equal sign, but it's not an equal operation. It's an assignment operation. It takes what's on the right-hand side and stores it into the left-hand side. Here, I'm clobbering. X is initially set to 4. So x is like a container. Actually, an integer is comprised of 4 bytes in RAM. 4 bytes taken together is used to represent integers normally. And that's what we do. We allocate 4 bytes, initialize the byte so it represents a 4. And then we turn around and say, no, I don't want a 4 in there. I want a 5 in there. So I overwrite what's in there, replace the 4 with a 5. So this replacing is also called assignment. So this is an assignment operator. It's an equal sign, you know, but it's an assignment operator. This is a less than sign, but it's an taken with the next one is an output operator. So don't think of this as an equal operation. It's not an equal operation. It's an assignment operation. Take what's on the right-hand side, store it into the memory or the internal representation of a number that's on the left-hand side. That's named on the left-hand side. Or we could do something else. We could say on the right-hand side, we could take x itself. Let's suppose we wanted to increment x. We could say I want to replace x with itself plus 1. We can do that. Now look at this. There's two operations here. There's assignment, and then there's addition. And the computer's not going to do two things at once. It's only going to do one thing. Which one is it going to do first? The assignment, or is it going to do the addition first? Addition first, yeah. So that's called an order of operations. So first, it looks at this, and it says there's a sub-expression. It's an expression that's part of a larger expression. That's also an expression. So for this expression to be evaluated, it requires that a sub-expression be evaluated first. So x plus 1 becomes 5 in this case. And that 5 is then written into x. So first we read the 4 out of the x, use it to evaluate this expression, and then write the result 5 back into x. There's the 5. And you'll learn there's different ways to do things. Here's another operation. This is the increment operation. This says whatever's stored in x, increment it. Add 1 to it. That's what plus plus means. Question?
What about x plus plus?
X plus plus? Yeah, that's that's also valid here. X plus plus is good too. You can do it like that. Now look, every time I do something, I run it. I verify it. See? I mean, I know it's going to work, but that's what you should do. You should be doing this, a lot of testing. See how I'm doing it up here? You know, I try something, I say the idea, you can think the idea, read it in the book, whatever. Discuss it with your friend, and then try it and look at it, verify that it does this. So you should be doing a lot of coding. You know, don't just read. You got to do the coding. You have to do the experiments. So get good at using whatever system you decide to use to do your programming in. You know, force yourself to start using it. And it gets easy after a while. You can see me, it's really easy, right? It's very easy. But you gotta just get into the habit of carrying out experiments as you're studying this material. All right. Well, there's a difference between plus plus this way and plus plus that way. Right? It's called a pre-increment. The other one's called a post-increment. And is that on the list? I don't know if I want to talk about it right now. It'll be on the exam, probably. Yeah, maybe I'll talk about it now. What time is it? I think we have enough time to do this. I'll talk about the difference between those two increments, because that helps in understanding expressions. So we have this, this value here. Let's create another value called y. We'll set that to 0. You know, in some languages, well, most modern languages, that's good right there. You can do that in this language too. But in C++ and C, there's no automatic initialization. So if you declare y like this without assigning anything to it, you don't know what y is going to equal. It's going to be whatever was in memory when memory was allocated to represent y. The memory is not initialized. Might be a 0, could be something else. Let's see what it is. Let's see if it's a 0. I'm just always curious to find out things here. It is a 0. What if I moved it to there? Am I going to get a 0? Still get a 0. But you can't guarantee it'll be 0. It might not be 0. But in more current languages, they will always, the compiler will initialize uninitialized variables to the natural 0. You know, like a string will be an empty string. An integer will be a 0, like that. A pointer will be a null pointer. That is those kind of things. All right, so a natural 0. And so we have this y value here. Now let's do this. Let's take x and set it to y. Okay? So x becomes y. So we print x, and it's just going to print 0. Let's check that. Now we get a 0 there. Trying to make the font smaller. Is the font too big? Well, not too big, but I can fit more on the screen if I make it smaller. It's the right size?
It is big, but we also want to make it.
Let me see what it looks like here. Is that all right? No, it doesn't work in there. Right, well, we don't need all that space yet. So what happens if we increment y, then we assign y to x and print x. Now we're going to print what? What? That's our hypothesis. Let's check that. What? What happens if we did post increment? What do we get there? Same thing. What? But do you see this expression right here? The expression evaluates to something. It evaluates to y. So we can use that here. I'll do it this way first. Now we're incrementing y. Now we have two operations. We have assignment and we have increment. There's two operations. So there's a battle. One operation is going to win out and go first. That's the increment operation. That has higher precedence. Say higher precedence. So first we're going to increment y, and then this expression, then I changes. I changes to 1. And then this expression itself evaluates to what y is, which is 1. And then that 1 is assigned into x. So we're going to print 1. There it is. Well, what happens if I did this? This is done a little differently. This is a post increment. So first, the value that y represents is used in the expression it's contained in. And then y is incremented afterwards. So you can think of it as the assignment happens first, and then the increment happens afterwards. Okay, so it's different. It changes the order of operation. The assignment, y is used in the assignment operation before it's incremented. And then y is incremented. So what does this print? This is like an exam problem. I said, what does this program print? Okay. So look at it now and come up with your answer in your head. What does this print? Any brave people want to say what it prints? What? 0. Yeah. Yes, I think it is. I'm wrong sometimes up here, by the way. So. What? Forgot to save. The world is back where I thought it was. For a minute there, I thought I didn't know anything. Okay, so that's how that works. That's called the difference between pre-increment and post-increment. Since you asked the question, I thought we covered it. Take a look at this this exam here. Exam 1. This is not working. I don't know what I did wrong here. Exam 1. Oh, no. It's not there. This is in... everything should be there, but it doesn't show up. So this will be like... it's not generating the files in that folder. There it is. It's there. It's just not displayed. I'm going to look into that. I'll fix that. So there's a problem right there. Problem 2. When the code in figure 2 runs, what does it output to the console? This is figure 2. This is the code in figure 2. When this runs, what does it output to the console? And look, there's n++ here and ++ n there. So you need to know how to parse this as if you were a compiler and then run it, in your head. Figure this out. You need to analyze this code. What does this print? Just to show you what you'll be expected to know how to do by the time you get to the exam. All right, I'll fix that link right after lecture. Now, there's still getting used to this. Now, integer is one data type. There's another data type called double. It's actually double precision floating point number. And we just say double. Another type is a float. So it'll be float y. And here we can do things, like 2.0, 4.5, like that. can be negative. So a float is 4 bytes in memory, and a double precision floating point value is 8 bytes. Usually, if you don't have a lot of data, you just use a double. But if you have a lot of data, like if it's like media, like if it's image data or video data or sound data, then the file is going to be really big. And if you can use a float to represent the data, then you'll save half the memory. So you'll see like things that are used for images and video and sound are stored using floats generally. So we print this. Let's see. Oops, it's clear. 4.5. Now what happens? We'll print y. We'll assign x to y, and then we'll print y. What does it print?
4.
Huh? What would a human would print? I'll make it even better here. What would a human print? 5. But what would a computer print? 4. Because a human is rounding, but the computer is truncating. It just discards the fractional component. And let's do that. Let's prove it to ourselves. It's 4. Oh my gosh. So there's a trick. If you want something to be rounded, what do? Does anyone know the trick? Yeah. Plus 0.5? Yeah, exactly. Just add 0.5, that's it, because you're going to truncate afterwards. So this will round. Right, watch this. You need to know that for one of the lab exercises. That's the trick for rounding. And it works this way in every language. Every language does this. Almost. I mean, some languages are not strictly data typed and then rigidly data typed. So variables can change their data type. So in those languages, you have to think a little bit differently. All right. What about strings? How about if I declared y to be not an integer, but a string? That means y is going to take character data. But this is not, the compiler will reject this. This is not character data. On the right-hand side of this assignment are numerical values, not character data. So let's see the compiler rejecting this statement. Error, conversion from double to non-scalar type string, and lots of other stuff in there. These error messages are hard to decipher sometimes, so we're going to be kind of like a detective and try to pull out some hints from what you see in the error message to know what's going on. But let's make it a string. I just put everything in quotes there. See, and actually the editor changed the color to green to show that it's a string. Now it compiled, and when we run it, what do we print? Think very carefully here. What do we print? Now, the computer is not, This is now being treated as simply a string of characters. It's no longer an expression. It's no longer a mathematical expression that's evaluated. It's simply a string of characters. So this is not an expression that's evaluated anymore. So when we print y, we're just going to print x plus 0.5. See that? This is a string of characters. This is an expression that's evaluated. That's different. And this is still valid, but it's not valid for string. It has to be an int, or a double, or a float, whatever it is. This is okay. Now, let me see if I can go backwards here. Now these strings, here we're printing the value of the string, x plus 0.5. But strings have attributes. They have characteristics that we can, strings have operations that we can perform on them. I'll give you one example. We can find out the length of the string with that expression right there, y dot size. Size is, I say, how many bytes are in the string y. So how many characters are in the string y? Not how many bytes. It's not bytes, it's characters. But this is a single byte character set, single byte representation of string, so it does equal the number of bytes. So what do you think this prints? Just make a hypothesis. Is it 4? I hear 6, I hear 4. The person who said 4, or the people who said 4, you're counting x and a plus and a point and a 5, right? 4 characters. But you forgot the spaces. That space is a character. Internally, internally it's represented by a number. Just like this point is internally represented by another number. So characters, all the information that's represented in a computer is represented using numbers. So we might see a character, but internally it's represented as a number. And a space is a character. And an ASCII character set, it's a 32. I know that. It's old common knowledge. It's this string is being represented with what's called a single byte character set. And that space, I know that the value that the space is equal to is a 32. All right, let's see. Well, we did. Let's prove this to ourselves. So, if we count the spaces, we're going to get 6, right? There it is. And there's other operations to strings. I can concatenate. I take, we'll set y to hello, comma, space. And then in the next statement, I'll replace y with y concatenated with Alice. So the result should be hello, Alice. What? Oh, that's the size. All right. That's 13 characters. let's do something different. Let's declare a variable name called name, right? Then we're going to do name equals Alice. Then I want to say, I want to form this string. I'll call it a greeting. Greeting is hello, comma, plus the name, plus a dot. Then I'll print the greeting. Now, these are variables that have, more than one character. So in math, all variables in math are one character. Right? When you run out of letters, you got to use Greek letters, and then run out of Greek letters, you're going to use something else. So, although you have subscripting and that kind of stuff and primes. But in computing, in programming, the variables can generally are given names. So you want to use something meaningful, like X and Y is not very meaningful in this context. But name and greeting, those make sense as variable names. So this should be hello Alice. Let's check that. Now, what happens if we don't initialize name?
You get an error? 0.
No, I think you get hello, comma, dot, because string is not a primitive data type like int. So primitive data types like int and double are not initialized. But string is called a complex data type, and it has an initialization. And it will initialize name to an empty string. So there's the empty string in there. See, an empty string is not a space. See the space here? That space is coming from there. Name has size 0. So it's not even a space. All right. Let's do this. Let's have the user type in their name. And we'll print, a greeting to the user. So let's prompt the user. We'll start. The first thing we'll do in the program is we're going to say, what is your name? I'll put a space there. Because I know that, oops, I forgot the output operator. I put a space here because I know that, it won't go to the next, not printing out a new line, so it won't go to the next line. Now, this program is not done. I want to test it. This is called incremental development. I know I didn't finish programming this, but I just want to test what I've written so far. I'm going to ask the user, what is your name? But I'm not going to perform an operation to read the name in. I'm just going to declare the name, form this string with an empty name, and then print it. So this is a partial solution. And this is called incremental development. I'm not trying to do the whole problem all at once. I'm just doing a piece of it. What is your name? Hello, comma, space, dot. All right, so I know I got this prompt to the user working. Now let's go ahead and read the name. So this is called the input operator. Like it's the opposite of the output operator. And cin is the name of the standard input stream. Cout is the name of the standard output stream. Compile and run. What is your name? Now look what happened. It didn't print hello. It says, what is your name? See, this operation here is called a blocking call. The program halts here. It's waiting for the operation to complete. And what the operation is waiting on the operating system to send it some data from the standard input stream. So it's waiting. So let's send it some data. Alice. And when I hit enter, then these characters will be sent through the standard input stream and read into the program. And then from the standard input stream, those characters will be stored into name. Hello, Alice. Now these streams are flexible. Watch this. I'm going to create a file. I'm going to do it down here. Call it test. Bob. There's a file called test and has the 3 characters in it, B-O-B, Bob. So when I run this program, I don't want the standard input stream to be the keyboard. I want the standard input stream to be the file test. So I'm telling the operating system that I want the characters that comprise the standard input stream to be the characters that are in the file test. See that? Not only that, but I don't want the standard output stream to be the console. I want the standard output stream to be a file called greeting. So these are redirection operators. You see the greeting right there? So that's how you change what the standard output stream, what the standard input stream represent. And you can set it to other things too, but I don't have a good example right now. All right. We get tired around 1 hour and we're like pushing it here. I'm trying to get stuff in by 1:15 and I know people are ready to go.
Can you explain, if you're done with what you were talking about?
Yeah, go ahead. I am done.
Exactly what, like why we need to say string name before we put input?
Oh yeah, here. Well, that's a very good question. Thank you. Look at what I'm doing right there. Do you see that? Look, the editor changed the color from black to green. This is a comment. This means a one-line comment. I commented out that line.
Like it ignores it?
Huh?
It ignores it then?
Yeah, it tells the compiler to ignore it. It's just for humans to read. Now if I save this and try to compile, it'll say name was not declared in this scope. The compiler is saying, I don't know what name is. What's name? So this line here is a declaration of name. It says what name is.
What does it say it is?
Now, take a look at this. What about this? Suppose I put the declaration down there. What do you think is going to happen? Same thing, because the compiler gets to hear. The compiler is reading the codes in order. Name is not defined. When it gets to this point where we're trying to use name, it says, I don't know what name is, hey, but we're going to tell you. but it says, I don't know about later. You know, I'm just looking at what you told me already. So it's going to say that name is undefined as well. By the way, other languages have different behavior, like JavaScript will work differently. Scripting languages in general.
Can you just like generally talk about what string, the command string does?
Well, this is a data type. So what we've seen so far is that we declare these names, like x is an integer, and y is a double precision floating point value. So you have the data type, and then the name of the data of that type. So this whole command here, this line, is an instruction of the compiler to create memory, to allocate memory to store a representation of a string. And we want to refer to that representation with the name name. Here, this tells the compiler, allocate memory to store an integer and have that representation or that storage named x. We want to be able to, you know, we're telling the compiler allocate a memory to store an integer, but then we got to give it a name. Otherwise, we don't name it, then we can't refer to it anymore. Allocate an integer and let it be called x. Yeah.
Where's the memory stored? Is it in the heap or the stack, or where exactly?
This is on the stack. There's two places. Memory is in two areas when the program runs. There's one chunk of memory allocated through the process. And that chunk of memory is divided into a stack and a heap. Huh?
Use new to allocate.
Yeah, new creates allocations on the heap. So that's an advanced topic. We're not going to get into that, but no, I'm happy to answer those questions, of course. What else? Any other questions? That's great. Made it this far. All right. We have other things in here. Boolean values. We'll talk about these next time. Okay. And that's it for today.